we present KMOPS, Keypoint-Driven Method, for multi-object pose and metric size estimation from stereo images. The objective of this work is to build a framework capable of estimating the 6D pose and metric size of all objects present in the scene from input images in a single forward pass. There are several challenges present in the existing methods. Monocular-based methods often require massive size datasets to learn spatial reasoning of the scene, but still suffer from scale ambiguity for accurate scale estimation. While RGBD-based methods are better at scale estimation, they often fail on reflective or transparent surfaces, where depth sensing becomes unreliable. Multi-view-based methods usually provide the best accuracy among all methods. However, they often assume a fixed spatial layout in their environment. This motivates our keypoint-driven, stereo-based approach. To address the previously mentioned challenges, we develop a keypoint-driven method with stereo image inputs to solve this problem. Our keypoint-driven method focuses on regressing 2D keypoints rather than absolute 3D coordinates. Therefore, our approach makes no assumptions on spatial layout and naturally supports image space transformations for data augmentation. Furthermore, a stereo setup offers a compelling trade-off between cost and performance. It leverages implicit depth cues directly from image pairs and ensures that most objects remain visible in both views. Leveraging the stereo input, our approach first extracts the 2D keypoints of the enclosing bounding boxes of the objects across both views and subsequently triangulates them to acquire their metric 3D positions. Then we obtain each object's rotation, translation, and dimensions by aligning the triangulated 3D keypoints to the canonical ones using a closed-form solution. The image encoder uses a shared RTDETR architecture, comprising a ResNet backbone and an efficient hybrid encoder for multi-scale feature extraction from stereo views. Left and right feature maps are concatenated and fused by multi-layer perceptron fusion blocks, enabling the transformer decoder to attend jointly to both views. After extracting image features, content embeddings are generated from the highest n number classification scores. We then construct n times k plus 1 queries by combining these embeddings with one instance query and k keypoint queries. These queries are iteratively refined through grouped self-attention layers, which separate within instance and across-instance interactions to reduce computational overhead. During deformable cross-attention, the model learns separate sampling offsets for the left and right view to facilitate better information exchange across binocular features. Finally, we triangulate the predicted 2D keypoints into metric 3D coordinates. By establishing correspondences with canonical keypoints, we recover the precise 6DOF pose and metric size using a closed-form weighted SVD alignment. We present quantitative comparison on the STARE OBJ1M dataset, which contains approximately 393,000 high-resolution stereo image pairs across 18 object instances. From the results, we can see that our approach sets a new state-of-the-art across all three DIOU and pose accuracy metrics. Methods using single RGB images like det-any3D, cube RCNN, and center pose struggle inherently with scale ambiguity. Center pose only bypasses this by cheating and using the true ground truth sizes during inference. While PTOR uses stereo inputs, its reliance on fixed spatial search boundaries hurts its fine-grained localization accuracy compared to keypoint-driven methods. Peter shows worse localization accuracy as it depends on handcrafted spatial bounds for 3D bounding box center regression. This limitation is evident in the percentage decreases from 10 degree 5 cm metric to 10 degree 2 cm metric, and from 5 degree 5 cm metric to 5 degree 2 cm metric. In comparison, we have a performance decrease of 7.6% and 10%, while they have 53% and 61%. Keypose fails in complex scenes because it relies on cropped regions to process one object at a time. Instead, Our approach unifies this by assessing the whole scene simultaneously. Our qualitative results also show that our method is more stable when it comes to estimating 6 degree of freedom object pose and size. One interesting thing to notice here is that while the visual results from cube R, C, and N might look better than center pose or date any 3D, the quantitative metrics suggest otherwise. This discrepancy emphasizes the inherent difficulty of reasoning about true scale from monocular images, particularly when high precision is required. We see this same phenomenon with PETR as well. In summary, we have 3 main contributions. First, KMOPS successfully unifies multi-object 6D pose and metric size estimation from a single stereo image pair in one forward pass. Secondly, by leveraging stereo depth cues and 2D keypoint regression, our method completely eliminates the need for predefined 3D search spaces or volumetric anchors. Third, demonstrated highly competitive and state-of-the-art results on the challenging TOD and large-scale STIR-OBJ-1M benchmarks. Still, there are limitations in our methods. Current reliance on known canonical object shapes limits generalizability to unseen categories. Future work will focus on relaxing this assumption. Also, while visibility scores mitigate truncation, explicitly addressing heavy inter-object occlusion remains a key target for future development. Thank you for watching. For more details and information, please refer to our paper and project page. We have also made our code available on GitHub. You can run a short demo easily with our code.